Good afternoon, this is Bill Langdon. I'd like to talk about my paper with Carol on improving parallel C++ Intel SSC SMD linear genetic programming interpreter. So this is actually one paper that's at this workshop. It's a follow-up paper looking at the AVX 512. So this is a more powerful version of the Intel vector instruction set. And both of these papers actually feed into a book chapter on long-term evolutionary experiments with linear genetic programming. So I'm not going to get time to talk about all three papers, but the goal really is why would we want to look at vector instructions, and essentially we want to speed up a long-term linear GP experiment. It turns out that the SSE 256 bits and AVX 512 bit instruction sets are very complicated. And so what we took was the manually produced version and then fed it into Magpie in order to run genetic improvement to optimize it. And as a result, we could run the linear GP system up to 100,000 generations in all the runs completed in less than 12 days. So I'm going to skip past the stuff about linear GP and concentrate on why we need speed. And essentially, for the full GP run, we want to 100,000 generations. We're looking at well in excess of 240 times 10 to the 15 GP operations. The initial approach was to try and parallelize the interpreter using the 256 vector instructions, which are available on my desktop. Manual coding proved hard and eventually was abandoned in favor of using multiple threads. But even on a machine with 24 threads available, this was not sufficient. And after the GPengine experiments were concluded, the reviewers came back and said, no, we really want 100,000 generations in all cases. And after that, we revisited the 256 bit experiments, and then AVX 512 became available. And so this I'm going to be talking about is the last set of Magpie experiments looking at evolving the linear GP interpreter, just the interpreter part of the linear GP system, using Magpie and concentrating on the more powerful AVX version. So again, skip past this. Magpie itself, there's going to be a tutorial later at this workshop. There are other tutorials which are online. And essentially the way Magpie works is we convert automatically the C++ code into XML. Magpie mutates the XML and then automatically converts it back to C++. So we have mutated code, which Magpie attempts to compile. If it compiles, it attempts to run it. We're essentially just taking the Magpie defaults and use local search. And for simplicity, all the runs run to 100,000 mutations, although in practice we don't need that many. And for each of the experiments, we're going to do 5 independent runs. So what we need of our GP interpreter is we want to do addition, subtraction, multiplication, and protected division on 8-bit read-write registers. So this is complicated because the AVX itself doesn't support 8-bit multiply. In fact, it doesn't have any division at all. So we can't easily do division of 8-bit data. And instead, what we actually did was to create a 256 by 256 lookup table. So we just look up the answer for protected division in that table. We're going to use the, as I said, Magpie to tune the human-produced code. And the fitness measure are essentially we run some test cases, and we measure how long it takes the AVX enhanced code to do those tests. And we're going to use Linux perf to measure them. So right, I'm going to skip past the compilation. One of the things in C++, access outside arrays is undefined. If you're lucky, if the mutant accesses data that it shouldn't, then you'll get a segmentation error. What we're using here is mprotect, which is a hardware solution that imposes no overhead. So the idea is if the mutant tries to read before the beginning of an array, it will go into these buffer zones, which are labeled protect_none, which will cause a hardware segmentation fault, and therefore the testing of the mutant will stop with a very poor fitness value. It's not totally foolproof, but it does seem to catch many things. In terms of the fitness test cases, we randomly generate test cases. We're going to run 4 small programs, and each of those programs is given 64 randomly generated test cases, which is supposed to run in parallel. So what we're measuring is the speed of doing all 64 simultaneously. And there are various rules. First off, we want to ensure the programs only read data with a defined value. In other words, data that's already been written. At the end, we want to ensure it generates an answer which is read out of register 0. And we want to ensure that all 4 operations, addition, subtraction, multiply, and protected division, are used. My expectation was that protected division would prove to be the most complicated. So what we insist is that it we test edge cases, in particular 0, 1, or 255. We also insist that the protected division kicks in, so we insist half our cases are involved with divide by 0. And then the remaining quarter, we want the output of the protected division to be uniformly chosen. And within those constraints, the rest of the program is chosen at random. What this graph is trying to show is at the back, it's a histogram of outputs from the test cases, assuming everything is working. It's in blue. You can see the special cases 0, 1, and 255 occur much more frequently than everything else. And in between those extremes, between those edge cases, the distribution of outputs is more or less uniform. So I said we run 5 independent Magpie runs, and in this experiment, well, in fact, in all the experiments, the output was surprisingly uniform. So here they generated exactly the same answer, and you can see that although each of the runs may take a different length of time, they all come to the same conclusion. So I'm going to skip past that one. Essentially, that is the mutation expressed as a patch found by Magpie. And what we do is we take that patch and apply it to GPengine's interpreter. And first off is Magpie has chosen to use unsigned char. It's not a big surprise since that allows the maximum use of vector instructions. In one case, it proved to be marginally faster to replace equality by greater than equal, which is entirely safe given that we know that the values evolved. And the other thing that probably makes the most difference is the two supporting routines, insta-arg32, which returns 32 answers packed into a vector, as does insta-reg32. Those are both called by the multiply routines. And what the equivalent of the Magpie generated patch is simply to remove all the code that masks a 16-bit answer down to 8 bits. And that's entirely safe because the following multiply code, which is the only thing that calls those two routines, is quite happy to deal with 16-bit inputs as even though it was designed to deal with 8 bits. And it provides its own masking so that the answer at the end is forced to 8 bits, regardless of the code that's been removed from the two support routines. Again, let me skip past this. And so to conclude, what we've shown is Magpie can automatically refine complex code that was difficult to code. Took several weeks in the case of the SSC256 and about a week for the later 512. Is produced small, compact, non-trivial, comprehensible, correct, and reusable patches. Runtime was less than a day. In practice, we could run it much faster than that, but as I said, we want to have a uniform set of parameters. Linux mprotect can help with the sandboxing, and it's useful in this case. As has been previously demonstrated, the Linux perf gives a very stable fits measurement in terms of how long it takes to code to actually execute. And the three independent patches generated by Magpie were applied to GPengine with no change in functionality. It just ran faster. And as a result, we were able to complete all the GPengine runs before the submission deadline. So at that point, I should really stop. Thank you very much.